So first, let me just say thank you to all the TNG people who have helped us so much. And I mean, there's clearly no way we could have done anything without an enormous amount of help. In particular, Yvette, who just introduced me, has been working with us the last couple of weeks, and Adriano in getting everything set up was critical. I'm going to tell you a little bit about laser frequency cones, as Yvette said first, to give you a sense of what we do, and then I'm going to tell you at the end some of what we've accomplished in the last couple of weeks. The Astro-Comb collaboration is, on our scale, what I think of as an enormous number of people. This is about as big a collaboration as I feel like I'm ever involved in. There's a set of physicists at the Harvard-Smithsonian Center for Astrophysics, a set of astronomers, and then some optical engineers from MIT who are critical laser people, and all of us together put this system together. And here on La Palma, in addition to myself, are Chihao Li, who's there, and Alex Glenday, someplace in the back, and Nick Langelier, who's a Harvard physics graduate student who had to go home to take classes. He left last week. So first, let me give you a little bit of motivation. I'm just going to say a couple of words in an audience like this. What we'd really like to do is find Earth-like planets around other stars, around sun-like stars. To find them using precision radial velocity, we need a sensitivity of something like 10 centimeters a second. And if you're looking for an Earth-like planet around a sun-like star, you're waiting for a year to see one period. So you need this 10 centimeters a second over a multi-year time scale. And that's a challenging program. In particular, there's 3 or 4 criteria that I listed here, including that one wants a collection of bright, low jitter stars to use as a target list. You want to observe them a lot. If you look at some of the work from HARPS-South, and there are literally hundreds and hundreds of nights of observations. You want a stable spectrograph, and you want a bright calibrator with long-term stability that can produce this 10 centimeter a second calibration over the span of years. And I'm here today not to tell you about target lists and how to figure out what the best low jitter stars are, or how to convince the director of your telescope that he should allow you to do hundreds and hundreds of observations of a set of stars. And I'm obviously not the person to tell you how to build a high stability spectrograph, but it seems like we know how to do that now. But I can tell you about calibrators. So what's an ideal calibrator? Again, it should have a lot of lines. They should be evenly spaced. They should be bright, and they should all be about the same intensity. Given that the dynamic range of our CCD is limited, having lines of orders of magnitude different brightness is not so good. They should span the whole optical spectrum, because we want to calibrate the whole spectrograph. And ideally, they would be traceable to fundamental physics, so that we know that if we calibrate today and we calibrate 5 years from now, it's the same calibration. And anything that's not traceable to fundamental physics is going to have systematic errors, and those systematic errors are likely to drift on multi-year timescales. And finally, you should be able to operate the thing at the telescope. And this, of course, for everything I'm going to tell you for the next 20 minutes or so, this is a very key criteria, and we're getting there. And so here's a picture, not from HARPS North, but instead from the trace spectrograph at the 60-inch telescope on Mount Hopkins in Arizona, showing you a 2D raw spectrum with thorium-argon lamp at short wavelengths and the laser frequency comb at long wavelengths. And you can really get a sense that we need a lot more lines, and they're a lot more, they're much more uniform in intensity. So what's an Astro-Comb? in my mind, it's composed of three parts. There's the laser frequency comb itself. This produces a series of calibration lines. However, for typical laser frequency combs, they're going to be in the near infrared, which is not where we want to calibrate, and so we need photonic crystal fiber or some other nonlinear element. And this nonlinear element takes the near infrared light produced by the frequency comb and turns it into light at the appropriate wavelength for calibration. And finally, we need some filter cavities, which are going to match the resolution of the resolution of the laser frequency comb to the resolution of the spectrograph. And I'm going to tell you about each one of these components one at a time. So first, the laser frequency comb. If we have a laser cavity with a pulse oscillating around in the cavity, then each time it hits the output coupling mirror, a pulse comes out. And these pulses are separated by the travel time around the cavity. In the case of the laser that we have here, this round trip distance is about 30 centimeters. And light goes 30 centimeters in about a nanosecond. And so each one of these pulses is separated by a nanosecond. If we think about that in frequency, and when I say frequency, you can just think wavelength if you really hate frequency. But as an atomic physicist, I tend to think in frequency. So if we take the Fourier transform of a series of pulses separated by a nanosecond, well, one of our nanoseconds is a gigahertz, so we expect a bunch of individual lines separated by a gigahertz. And the shorter these pulses are, the more spectrum we get. And so what we want to make an ideal calibrator would be very, very short pulses to have broad bandwidth and very rapid repetition of pulses to make the spacing between these as big as possible. And in practice, it turns out to be really, really hard to make anything much faster than about a gigahertz. Maybe, in the lab, we've been demonstrating about 3 gigahertz. Commercially, this sort of laser, about the fastest you can buy, well, is the gigahertz laser we have. More typically, they're 250 megahertz. So now, if I show you this picture, you say, great, we're done. Look, we got a bunch of lines. I can stabilize the separation between these lines just by taking a little bit of this light and shining it onto a photodetector. On the photodetector, I see pulse, 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 pulse at a gigahertz. And if I measure that and I compare it to some nice RF oscillator, I can stabilize the spacing, and away I go. But now there are 3 problems. 2 I've already told you about. One is that this is actually in the near infrared, which is not where we want to calibrate. Another is that a gigahertz this gigahertz spacing is too small to be resolved on spectrographs, which is like white light to the spectrograph. The third thing is, and this was something that bothered laser physicists for many years, is that in fact, if you were to look at this, if you built a super high resolution spectrograph and looked at this light, after stabilizing the repetition rate, you wouldn't see a series of lines, because if we come down to this corner of the graph, we can see that there's an offset. Each one of these lines is not, in fact, equal to just an integer times the repetition rate, but in fact there's an offset. And that's because inside the laser cavity there's dispersion. And these pulses are really short, so they're composed of many frequencies, and if you have some dispersion that you go through repeatedly, that leads to a frequency. And so we need to stay, and so that frequency can drift as the apparatus changes. The apparatus warms up or something, and so these lines spread around. And so you end up with this white light. And so what do we do about that? Well, we go to talk to our friends Ted Hench and Jan Hall. They won the Nobel Prize in 2005 for figuring out how to solve this problem. If you can make a short enough pulse, and pulses coming out of our laser are something 4, 5, 6 femtoseconds long, That's a little bit more than one optical cycle. It's maybe 1.5 optical cycles underneath our pulse. So when I draw pictures like this is actually wrong. There's not that many cycles of the light. Our pulses are shorter than this, which is kind of fun. So what they won the Nobel Prize for was realizing you make short enough pulse that you have an octave, a factor of 2 in frequency worth of light. You can compare some blue light, or really this is 600 nanometers, but for purposes of this laser frequency comb, we'll call it blue. Excuse me, I went the wrong way around. Start with some red light, some low frequency light that's now 1200 nanometers, and we frequency double it, and we compare it to some high frequency light at 600 nanometers. We can beat them on a photodetector and measure the difference. And if you work out all these n omega plus omega offsets and n omega plus omega offset, you double this one and you subtract and you make n here equal to 2n there, all that's left is the offset. And you might want to write that down yourself if you actually want to figure it out, but double this, compare it to that, and it tells you the offset frequency. And so now you can measure the offset frequency as a beat node on a photodetector, and you can measure the repetition rate as a beat node on a photodetector, stabilize them both to RF synthesizers, and now all these cone lines are stabilized. And even the Nobel Prize for good measure. So that's a laser frequency cone. And ours is actually a high sapphire laser in a bow tie cavity, and you can't really see this, but this is what the thing looks like. The cavity's in here, there's a pump laser to actually pump it, and the optics down in here are the things that measure that offset frequency and repetition rate. They're separated by about a gigahertz. There's about 100,000 lines, and it's between 6,000 angstroms and 10,000 angstroms. So now let me say a couple, and this was the high-speed introduction to laser frequency cones. Now let me say a couple things. One, I keep saying gigahertz, and you guys probably, if I say, you'll say, what's a gigahertz? I know how fast it is on my computer. I don't have any idea what it is in terms of the spectrum. Well, there's a little cheat box that I'll put up in most of my slides. A gigahertz is about a picometer in the green, and it corresponds to about 550 meters a second. And so it turns out the resolution of HARPS-N is about 5 or 6 gigahertz. So again, this would look like white light to the spectrograph. So we need to thin out these lines. And we've got a long ways to go to get from even this 550 meters a second down to 10 centimeters a second. And the other piece that I get to say is that we measure all those frequencies, and we stabilize them with some frequency synthesizers, and those frequency synthesizers are now all locked via an atomic clock with the GPS. And so we know absolutely that if this line is 550 terahertz, we know it out to 12 significant digits. And 12 significant digits is more than enough to get to 10 centimeters a second. So intrinsically, all these lines are stable enough to get us to the 10 centimeter a second line. So that's the laser frequency cone. And so one of the reasons that we call this instrument that we brought here an Astro-Comb and not just a laser frequency cone is because there's more of my talk left to come. Having a laser frequency cone is not enough. You might kind of think that it's the part that won somebody a Nobel Prize, but there's still more work to do. So now I'm going to tell you about taking this near infrared light that comes out of the laser frequency cone and converting it to something useful for the spectrum. And I'm not going to tell you very much. Just what I want to say is it's magic. And you can see this magic in action up here. There is this optical fiber, and you can see scattered light from the optical fiber coming out. We put red light in on this end, and the red light propagates through and it becomes green. And really what's happening is that the cross-section of the fiber looks like this illustration on the upper right. There's a bunch of air holes inside the fiber, and there's a very small core. And if you get all the light into the core, and you have femtosecond lasers, so the instant pulses are 5-6 femtoseconds long, you get very, very high peak intensities inside this photonic crystal fiber. And the intensities are so high that even silicon, which you would normally think of as the most inert linear thing, if you want to pick a material that's linear, you would pick silicon. But we made peak intensities so high here that even silicon is nonlinear. And then we basically get four-wave mixing, in which if I have two frequency keys with my laser frequency cone, they can mix due to four-wave mixing inside that fiber and generate another tube separated by that same frequency. They can then propagate a little bit more, and these two teeth can mix and produce another line. So it can walk out and generate a whole broad spectrum. And that's photonic crystal fiber. You've got to do it all right, and there were a bunch of tricks. And I could talk about, or we could make Chi Hao talk about the tricks for half an hour easily. But I'm just going to say it's a nonlinear process that's coherent. And look, you can see it in action up there. The one we actually use here is, instead of being that long, it's actually about 6 millimeters, 7 millimeters long, and it sits inside this little housing. Here's the spectrum. The blue line is what comes out of the laser, and the red line is what comes out after the photonic crystal fiber. And here's 500 to 600 nanometers. We were way down low, now we're up high. So this is good calibration line. These are all on log scales. And so I said back at the beginning of the talk that one of the keys to making a useful laser calibrator was that we had even intensities. And so if I showed you something on the log plot, you should pretty nearly just dismiss it out of hand as being completely useless. Because if I had to put it on a log plot to show it to you, I'm not calibrating it. And so very quickly now, we're going to zoom in on this part, and I'm going to go to linear scales. Finally, filter cavities. A gigahertz is about a fifth of the resolution of the spectrograph. How do we how do we actually make lines that we can resolve in spectrograph? Well, we use conventional fabric Barreau cavities, two of them in series, and they're very carefully fabricated so as to be exactly resonant with, in this case, every 16th line from the laser frequency cone to match to get something that's about 2.5 resolution elements, which lets you nicely see the wings and be able to fit and model and get good calibrations. So once again, if we look here at the output of the photonic crystal fiber, we see a whole bunch of lines. If we look at the filter cavities, here's a schematic representation of the resonances of the cavity, and they're all nicely lining up on lines of the cone, and then there's a bunch of them in between that get filtered out. And so now we have a nice set of lines that we can use to calibrate them. The mirrors inside the fabric Barreau cavities are dielectric multi-layer mirrors. One of the tricks that we use to improve the bandwidth of our calibrator is something that our MIT colleagues have named complementary chirp mirror pairs. You can kind of think of them as it's schematically drawn here, that there's a set of layers of differing thicknesses that cause different wavelengths to be reflected, depending upon the wavelength that'll penetrate different depth into the dielectric material. And that penetration depth difference is enough across 100 nanometers to cause the cavity to become out of phase with the laser frequency cone. And so what we do, crudely speaking, is to take one of these mirrors, take this set of conians, and flip it around. And so now on this mirror, the red penetrates deeply. On this mirror, it penetrates less deeply. And blue penetrates deeply on the other one, and less deeply on this one. And so now, over a much broader wavelength range, we can get the same penetration depth on the average over both mirrors, and thus have the same effective cavity. And that's a complementary short mirror pair. One of the issues with them is it means it costs twice as much as a more conventional system, because here both mirrors are the same, and so you can just dump a bunch of substrates into your oven and lay down the coatings and you're done. Here, well, you have to do 2 mirror coating runs, and 2, Chi Hao has to remember, oh, I took 1 left-hand mirror and 1 right-hand mirror. He has 2 left-hand mirrors, it's going to work. And they never let me take the mirrors out, so I don't actually know even how they're marked. But this was a technique that we've developed to make the Astro-Combs work. It was much more optimal bandwidth. But still, we can't cover all of HARPS-N with 1 set of mirrors. And for those of you who've been paying attention to all the excitement of white light fabric growth cavities, which are a much easier system than noise frequency cone, you can basically just go out and buy a bright white light source and run it through a passive cavity. I thought I might say a few words about some distinctions between what our cavities do and what a white light cavity does. One of the issues with a white light cavity is that you basically see the full line profile of the cavity when you shine the white light. The white light is just telling you what the response function of the cavity is, and so if the cavity changes length a little bit or changes alignment a little bit, you'll see these lights move around. That will choose a systematic error in your calibration. And so one of the things that people work very hard with to make white light etalons is to really make them thermally insensitive. Do lots of compensation tricks to really try to reduce the temperature sensitivity. That's much less of an issue here because instead of white light, we have a bunch of delta functions. And as long as the line width of the cavity is small compared to the spacing between lines, then basically you can think that you don't really care if the filter cavity drifts a little bit. If the filter cavity drifts a little bit on the line, well, the intensity that comes out the other side changes a little bit, but the frequency is still the frequency of the input line. Now, that's kind of 99% true, but in fact, the nearest mode is only about 5 line widths away or something like that, and so it's suppressed by about 23 dB. And you might worry about a factor of 300 suppression not being enough when you're trying to do 10 centimeters a second X over astronomy. And so we put 2 cavities in series, and we get something greater than a factor of 10,000 suppression in the line. So then we really don't care. And it's really just this main line that actually comes through that we see on the spectrogram. The final piece that wasn't in my list of 3 key things, but it's kind of fun nevertheless, is that our laser is a coherent source. And that means that we have to worry about interference from the coherent source. In particular, as light from the laser, light from the comb, goes through the fiber that feeds HARPS-N, that fiber is a great big multi-mode fiber, and there are lots of different paths that the light can take. If you really wanted to analyze this correctly, you'd get into decimal functions and all kinds of complications. But from a simple perspective, this drawing kind of gives you a flavor. You can imagine that there's a path where the light just goes straight down the fiber, and there's an extreme path where the light just barely is in the acceptance angle of the fiber, and it takes a much longer path. And now, if these are both light from a laser, they're coherent, and now on the output they can interfere. And I worked out some math, but we don't care. Here's a result. Once again, this is data from trace, but I'll show you in a few minutes data showing the same thing from HARPS-N. And I'll explain to you how we actually make this picture. But let me just tell you that this is a bunch of Astro-Comb lines all superimposed on each other. And the black line is with the shaker on. And the shaker basically just, let me show you the shaker now. This is the HARPS-N shaker in action. So this orange thing running through the middle of the picture is the optical fiber coming from the laser comb before it goes into the fiber that goes to HARPS-N. We were a little bit scared to do this to the 600 micron fiber that goes to HARPS-N. But this is basically just a hard disk head. In here is a hard disk head that we've taken apart and mounted up in a nice way, and you can see it shaking the fiber. And it's kind of bending the fiber. I sent this video to my family, and I've gotten more jokes about martinis and daiquiris than you can imagine. So you can't really see it here, but there's the shaker. When we turn the shaker on, it bends the fiber, and all these paths change, and we can average over the coherence. We wash out the coherence by changing all the path lengths. And so now when we integrate for a while on the spectrograph, we get this black line instead of the much bigger variation red line that was with the shaker off. And so this improves our signal-to-noise ratio, which is important. So that's the Astro-Comb. Now, this is a joke for the hard work that Adriano did to help us. Here's the Astro-Comb. Here's HARPS-N. Now all we need is a fiber to get us between them. And this turned out to be a little bit of a crisis for about 24 hours where I was terrified. We actually ordered a replacement fiber from the United States. The last we heard, about a week ago now, when this crisis happened, the last we heard it's still in Madrid. Happily, Adriano saved the day and found a spare fiber that was just long enough to reach from the Astro-Comb to HARPS-N, and we were in business. So one of the first things we did was to go observing. Emilio was generous with telescope time, and the scene wasn't so good, so I don't think we really wasted anybody's time. And that's like, we're busy learning things, so if we didn't get the most pristine night that the observatory has ever seen, that's okay. So we got some spectra of Vesto, calibrated by the Astro-Comb, and what we would like to do is to use this Vesto spectrum and data that Alex and Chiha have recently taken in the lab back at the Center for Astrophysics of a solar spectrum that's calibrated with the laser frequency comb to try and do an improved accuracy assessment of the TNG and HARPS-N with the Astro-Comb. That's going to be a lot of work. I'm not here to report any astronomical results or anything. I just wanted to show some since we took them. But we're going to go home and think very hard about how to really do this. Instead, I want to tell you about the calibration. So here is about 120 nanometers of calibration light from the Astro-Comb. And again, this is the full calibration. This is the full bandwidth of the spectrograph, so you can see we're not quite covering half of the spectrum, but we're pretty proud that we can cover this much. In order to do this, we really need those fancy mirrors. You can see that I'm now on a linear scale. And I'm not perfectly flat, but I'm pretty good. If we go look, actually I can draw this arrow all the way to here. If we go look in here, here's what we see. A whole bunch of lines. They're all evenly spaced in frequency and nearly the same amplitude. Now, how well can we calibrate from those lines? Well, there's a pretty simple formula that's the flow of the half max of the lines, divided by the signal-to-noise ratio and the number of points across the peak. That tells you how well you can determine the center of one peak. If we plug in some numbers, we get 4.3 megahertz is the uncertainty in one peak. And what's a megahertz, I hear you cry? Well, it's 1,000th of a gigahertz, so it's about a half a meter a second. So this is a couple meters a second in one peak, which is pretty nice. And since the resolving power of HARPS North is so high, we get about 350 peaks across order, and so ideally we would be at 10 centimeters a second already in one order. All these numbers are purely photon shot modes. This isn't how well we've done. I'm going to show you what we're doing now, but this is where we should be if we could understand all these peaks at the photon noise level. And this is another reason why the shaking is so important, because shaking will ruin photon shot noise limits. Instead, we'll be at pattern noise from the speckle will limit our signal to noise ratio, and probably limit to about a 10%. So, all right, let's go and try and actually model the response to the spectrograph. We've got, we know what the cone does. We know what the spacing is. It turns out all these side modes are completely negligible. They're suppressed so well by the filter cavity that we don't have to model these next lines. Another way to say it is this little cartoons on a log scale diagram. So forget all of those. We then in our model of the spectrograph, we include the fiber, which we model as a half circle with some skew. We model the optics as Hermite-Gaussian polynomials. We use a lot of them, and we allow their ratios to vary across the order. It's a complicated model, but it works really well. And so here's one order out of the standard DRS pipeline, and the error bar as well. Alex has plotted this for me, so that you basically can't see the error, the residuals at all. But if I show you the same plot for the shaker off, you see the residuals. It makes a big difference. But we're fitting this very well, and I'll show you more in a second. Okay. So now if we look at what happens from what the fit model is telling us, the fiber component of the fit model in these plots is black. The optics are in red. These Hermite-Gaussian polynomials in red. You convolve them to put them together, and that's this kind of olive green color. And I'm showing what the fit says the light profile looks like for the leftmost peak of one order, the center peak of one order, and the rightmost peak. And you can see that the fit really doesn't think it's Gaussian. The fit shows all kinds of weird asymmetry and long tails and all kinds of weirdness. And these fits came out yesterday. Came out of Alex's fitting routines yesterday. So I don't want to swear to anything today. And if Christophe or Francesco are listening, I'm going to email them to talk. And even if they're not listening, I'm going to email them to talk, and I would love to know what they have to say. If they think we're crazy, if they say, oh yeah, of course that's what we're seeing in thorium argon. I don't actually know yet. So you guys are the first to hear. These are the weird PSF responses that we're seeing with the Astro-Comb. Just to give you a sense that this isn't completely crazy, here's one line. And I've swept a whole chunk of how we make the Astro-Comb work under the rug, which is that in addition to the comb, there's a CW laser, and we lock the CW laser to the comb, and then we lock the filter cavities to the CW laser, and that gives us a more flexible, reproducible control over the exact frequency of the cavities. But here's just that CW reference laser with no comb lines in place at all, showing you that things are kind of asymmetric. This is on a log scale again, so we're getting way down to the tails here. And actually, this line is very close to the center. So this is one of the more symmetric responses to spectrum. But this just gives you a sense of what's coming out of the Astro-Comb calibrations in terms of itself for HARPS-N. And so now let me conclude here by showing you how well fitting is working. And this just takes a little bit of explaining. What I'm showing you here is all of the Astro-Comb lines of one order superimposed on each other. We take the results of the fit, and the fit tells us where the center of each line is. The fit also, and so we line them all up on top of each other. The fit also tells us what the amplitude of each line is, so we normalize all the amplitudes. And the fit tells us what the width is, so we rescale the x-axis for each p, so that they all line up on top of each other. And that's what we're showing here. The red lines are the data, the blue lines are the fit, or vice versa. So they lie on top of each other, so I can't remember which is which. Here are the residuals of the fit, and that they kind of look like a galaxy is coincidental. It's really just showing you that where there's more counts, there's bigger absolute uncertainties, because it's roughly photon noise statistics. And to show you how close to photon noise statistics it is, the middle graph shows you the ratio of the measured residuals divided by what we would expect from photon noise. And on peak center, we're within about 10% of photon noise. And out here in the wings, we're getting up to 1.8, 1.9 times photon noise. So we haven't quite gotten these wings exactly right, but we're getting very close to photon shot noise. So at this point, we're ready to start looking at the wavelength solutions and actually tell you how to calibrate that fiber of the spectrograph. But if I go back to all this skew and asymmetry, you might worry how to really apply a wavelength solution that comes out of this nearly photon noise limited calibration with that kind of 10 centimeter second accuracy, because there's every reason to believe that this skew is going to make it challenging to really apply at the 10 centimeter second level. But that's stuff that we're going to go home and work on. We have about 1,000 Astro-Comb spectra at this point, and we're still here for a couple more days, so we'll probably have 1,500 Astro-Comb spectra to process through this and start to get a feeling for how reproducible things are. And really, I'm just showing you results from one order. And late last night, Alex was looking at another order and seeing things being a little bit different. So this is all very preliminary and very much work in progress. But this gives you a flavor for what's coming out of the Astro-Comb and HARPS-N. Oh yeah. And so one last slide. Just to show you that the shaker's a big deal, if you turn it off, it always gets a lot worse. So it's really important that you destroy coherence of the laser. And part of why I showed you all this is, of course, that we learned this the hard way. We spent several weeks in Arizona just not understanding why we were getting such terrible residuals. And then at some point we realized, I forget how we realized it, but we realized, oh, coherence could be a problem. And so we put a shaker together, and then everything worked beautiful. And I got this email from Alex, who was back at Cambridge writing his thesis at the time, saying, photon shot noise! And we all danced, and we were happy. So still here 3 years later, 3.5 years later, I'm still showing you, look, the shaker's important. So with that, I will conclude. And this is a very beautiful island, and every evening when we get home and we see the place we're living in Figueroa for the 3 weeks that we're here, I love the sunsets. And thanks to Adriano and everybody at the TNG who kind of hold the floor to lower the table in. Wow. Okay. So thanks to all of them very much, and thank you for listening.